Rotational motion problem solving. We'll start with an unwinding spool of string, then a rolling sphere, Atwood's machine pulley with moment of inertia, sphere on an incline, rolling sphere and incline, dart and a bicycle wheel, disc and rod collision, and a rotating rod. Unwinding spool of string. We have a spool of string over here. It's wrapped several times around the rim of a spool that has a radius 0.025 meters and a mass of 0.015 kilograms. The free end of the string is attached to the ceiling, and the spool is released from rest and unwinds without slipping on the string. We have your moment of inertia of the spool right here. And the first thing you want to do is show all the forces on the spool, and you can use that diagram there. Find the acceleration of the center of the spool when it descends as the string unwinds, and hopefully you can visualize what's going on here. So let me just erase this. And basically this guy is rotating in that direction as it's falling down, and the string that's in here is then just going up like that. So at some other point it'll look like this. Okay? Find the tension force in the string. Then how long does it take for the spool to descend 1 meter? So obviously there's at least 1 meter of thread on the spool. And then calculate the angular speed of the spool after it has traveled 1 meter. Here are the forces, and in the past when we did free body diagrams we just had a dot and we'd put all the forces on it, and if we had multiple forces we'd kind of draw them out like this, or you could stack them like this, but the whole point was we just had a dot. But now we have to take into account the actual physical dimensions of what's going on here. So our free body diagram looks like this. We have gravity acting on the center of the mass of the spool, so we draw that in the middle. But then we have this tension force acting on the edge of the spool, which will provide a torque. Note, this does not provide a torque because it's acting at the axis of rotation. The tension will. So this is the answer to A, that picture right there. To find the acceleration, we need to set up simultaneous equations for both the linear and the rotational acceleration of the spool. And we're going to split it like this. Above that line are the linear functions and below is the rotational. And then we have to come up with a convention for the sign. So what we're going to say, this will be the positive direction for our acceleration because it's accelerating downwards. And then what kind of rotation lets you accelerate straight down? Well, the spool's going to accelerate that way when it's moving down and accelerating in the down direction. So we will choose a clockwise rotation for positive alpha. So let's do the linear equations first. We sum the forces in the y direction, and from our free body diagram we have mg down and tension up. So that will give us a negative for the tension, positive for mg, and we divide by the mass of the spool. So then we just go ahead and do a little algebra and we come up with this equation. For the angular acceleration, that's equal to the sum of the torques over the moment of inertia. So our torque is provided by this tension force acting in that direction, which will tend to give you a clockwise rotation. So that's in the positive alpha direction. So our torque will have a positive identity. It'll be T times R, the tension times the distance from the axis of rotation. We then substitute in our moment of inertia. That was given here because we are rotating about the center of mass of the spool. Do a little algebra and we have our second simultaneous equation. Here's our two equations from the previous slide. We have the linear and we have the rotational. We'll work with the rotational first. Since the spool rotates, moving downward, and the string is not slipping, we can make this substitution right here in equation B. So instead of alpha, we're going to have A over R. So A over R, and it goes over to there, equals T over MR, and that tells us that tension is equal to MA. Now we take that value and we substitute T equals MA into equation A. So we have right down here, A is equal to G minus MA over M, We cancel out the m's. We find that a is equal to g over 2. And here you can see we're using 10 meters per second squared for g. 9.8 of course is more accurate, but for the APC exam you're allowed to use 10. And so we get an acceleration of 5 meters per second squared. Find the tension force in the string. Well, we already have an expression for tension. It's just equal to ma. And then we plug in our value for the acceleration found on the previous slide, and we get the tension is 0.075 newtons. How long does it take for the spool to descend 1 meter? This is a linear distance, so we're going to use a kinematics equation in the linear notion, right? So that's just y in the y direction. So we want to go 1 meter, so our final distance will be 1. Our initial is 0. We're setting where we start at 0, totally free to do that. The initial velocity is 0, and then it's just 1/2 at squared. So t is equal to the square root of 2 over a, and be very careful here. Make sure you use a equal to 5 meters per second squared as we found in part B. Don't use the value for g here. You may have done that automatically because it's falling, but you are not in free fall here. You've got a moment of inertia on the spool, and that's contributing to the fact that we cannot be in free fall. So we put our 5 in there for the acceleration, which is half of g, and we see it takes us 0.63 seconds. Calculate the angular speed of the spool. So what does that mean? We're looking for omega, not v. So to find that, we're going to need the angular acceleration. So angular acceleration is linear over r. R is the radius of the spool, and we find out that that's 200 radians per second squared. We then use our first kinematics equation for rotational quantities. So omega is omega 0 plus alpha t. It's initially at rest, so omega 0 is 0. We substitute in the numbers we found in previous parts of the problem, actually the exact slide before us, and we have the angular acceleration here, and we find omega is 126 radians per second.